All right, this lecture is going to be about animation and video. So, first of all, video starts with animation. Let's talk about the premise of what animation is. The most fundamental principle of animation is the persistence of vision. Persistence of vision is the visual illusion of movement. So, when you see sequentially altered images rapidly changing over time, your brain maps them together, filling in gaps to see movement, as you see in this particular slide, which we're going to talk a little bit more about this later. So one of the earliest instruments of optical illusion that used persistence of vision is called the zoetrope, and it was created by a mathematician named William Horner in 1833. Similar kinds of little things like this have been around for a really long time, but this is one of the sort of recorded, official inventions, I guess. But if you look back in a lot of other kinds of folk things, you might actually see some things that look very much like zoetropes. So let's look at some examples, for instance. Okay. Let's just watch this really quick video.
One way of animating pictures is with a zoetrope. And check it out. Here's one right here. And it's got a little thing that makes it turn. And then there's a little, probably cardboard thing with little slots. And inside you can see there are pictures. And when we have it spin, you can see that the pictures are moving around. And it doesn't really look like much until you look through the little slots. And then now we've got a bunch of birds flying. And that's a zoetrope.
Zoetropes go back to the 19th century. If you imagine a barrel with little slots and images, each a little different from the last, it's like a shutter, and it shows you a little glimpse of that drawing across the way, and they appear to move. Studio Ghibli has this amazing three-dimensional zoetrope. John Lasseter had seen the zoetrope there, and I think he said, I've never seen an object that so well describes the basic premise of animation. When it was suggested that we do one for ourselves, it was a no-brainer. Instead of drawings, we're using sculptures. So what you're seeing are 18 different sculptures, each slightly different than the last one. And instead of flipping through them, we're using a strobe light to make those images stick in your eye. And these spinning images freeze in space. And each sculpture replaces the last one and appears to move. It's stunning because it looks like it's come to life right in front of you.
I think that the zoetrope is the clearest explanation of animation, because on the disc, you get to see every frame of animation before your current frame where you're looking, and every frame of animation after it. Here you have the opportunity to see the tricks the animator used to make things move.
It's a very simple mechanism, it's a very simple idea, but somehow seeing that come to life right in front of you is really fantastic.
Okay, so now that we've looked at some different types of zoetropes, all the way from traditional to three-dimensional formats, let's talk a little bit about the origins of animation. So the current slide, what you're looking at right now, is Edward Muybridge's study of a moving horse, which is considered to be the first official moving picture. Muybridge was commissioned by a racehorse owner named Leland Stanford. He actually was a governor of California. Anyway, he was commissioned by Leland Stanford to prove Leland's hypothesis that horses have all hooves in the air at the same time at some point as part of their gallop. And so what's amazing about this is that you should remember that cameras use single plates at a time. So this was quite a feat. He had to set up a battery of cameras with electromagnets, releasing each camera shutter at a specific interval as the horse passed. And they did this at a racetrack. I think it was in Pittsburgh. Anyway, or yeah, and University of Pennsylvania, I believe. Anyway, and so this Muybridge study was done in 1878. So if you can imagine, that's like pretty amazing. Each shot was taken less than 2/1000ths of a second apart. The thing that makes that really incredible is that the if you think about digital cameras today, it's not that big of a deal. But if you think about the kinds of cameras that they were using back then with these big plates, and having to time them just exactly right is pretty incredible. And the reason that you see the grid in the background is because of the way that they had to like set it up mathematically and so forth to capture everything. Anyway, and so that's what it would look like. And the bottom was a series of woodcuts, the bottom one, that he made based on those photos. And you can follow this web address if you want to check it out, University of Pennsylvania. Okay, and that's the woodcut. And he published this work in 1882, and he used this work as the basis of his zoopraxiscope invention. Okay, so zoopraxiscope. Muybridge first demonstrated his zoopraxiscope to the public in 1882. It's often quoted as the first ever moving picture. Basically, it's a little glass disc with painted photographs in sequence, and he projected light through it to a screen. Okay, and that is what led to this, the kinetoscope, which is invented by Thomas Edison. And so he actually cites Muybridge's idea as the foundation for his invention, which is actually pretty amazing considering Thomas Edison stole a lot of stuff, actually. But it was a projection device using perforated film to move through images, or to move images past a peephole for a single viewer to be able to look into an eyepiece and watch. Okay, and this is sort of how we ended up getting to. There were some other inventions after that, but this is sort of how we eventually got to film. All right, film is produced in this way, where images are captured at a rate of between roughly 24 to 30 images per second. We refer to that as frames per second, or FPS. The human eye can typically not see anything faster than 30 frames per second. And so if you can imagine, that's an awful lot of individual single images in order to get animation. Okay. Let's also talk about some newer animation techniques. We'll discuss cell animation and computer animation. So cell animation is where a distinctly separate graphic is represented in each frame, okay, or still image of an animated sequence. And the word cell comes from celluloid film, which is what film was once made from. Okay, so that's where the word cell comes from. And this is the most traditional form of animation. Right. And so cell animation concepts, some really important ones are keyframing and tweening. Okay, so keyframing and tweening, basically in cell animation we have keyframes that determine the start and stop points of major visual changes. The frames that are rendered in between to transition the changes are referred to as tweening or in-betweening, right? That's where it comes from, is in between. They're referred to as tweening frames. Okay, so That's incredible, right? If you think about it, in traditional hand-rendered animation, all tweened frames must be hand-rendered. That means that every one of those still frames in between must be hand-rendered. You know, imagine, that's supposed to say imagine, not imaging, but imagine 24 to 30 images per second of film. That is staggering when you consider like some of these feature-length movies, that were produced like in the 50s, like Fantasia, and even in cartoons and stuff. That's millions of drawings. Okay, this is actually the first animated cartoon, Phantasmagoria, in 1908. This is actually pretty interesting if you would want to kind of check it out. Okay, and that brings us here to computer animation. With computer animation, most tweening can be automatically generated by the computer, although important keyframe elements must be considered to make sure that the computer interprets the changes correctly. So for instance, in a traditional animation with a moving object along a path and changing direction, size, and rotation, you would want to draw several hand-rendered keyframes to indicate, where the major changes are, so that you would know how to visualize and draw the frames in between, right? Well, in vector-based animation, okay, this is where computers come in, you can potentially have two keyframes, beginning and end, to do a lot of those same things, whereas traditional hand-rendered animations might need many keyframes, right? And objects' properties can be mathematically altered as it moves along a vector path between two anchor points in computer animations, referred to as like motion tweening, shape tweening, so forth. So let's take a look at that.
I'm going to use Flash really quickly to show you a very simple demonstration of some of the differences between the way that you would have to do tweening with keyframes in regular hand-rendered cell animation versus the way that we can do this kind of keyframing and tweening in computer animation, because there are some differences. Even though the concepts are very similar, if I wanted to move this object, let's say I wanted to have it do sort of like a path like this or something. I wanted to have some sort of path, all right? If I wanted to create an animation that would do that, in regular hand-rendered animation, then I would need to do something like have a keyframe at the starting place. I might need to have one here. I might need to have one here. I might need to have another one somewhere around here, and then a last one up here, so that we could see visually where the paths were, so that we would know, or, where the path was set out to be, so that we would know how to render the drawings in between. Well, with computer animation, I really only need two keyframes. I need the start and I need the end. And then what I can do is I can draw a path that I can translate, and it'll do mathematical translations for me, so that it can make all those changes just using two keyframes. Okay, so what I'm going to do is I'm going to right-click down on my timeline. You see right now I've only got one frame. I've got my object on the stage in one frame. And I'm going to go ahead and I'm going to say create a motion tween. And then you see automatically what it does is it pulls this out to 24 frames, to the 24th frame, and it puts the playhead on the 24th frame. That's because it's suggesting that I have a 1 second animation, because it's doing 24 frames per second. So while my playhead is on that last animation, I can create a keyframe by dragging it to a new location. You see it puts a dot here. All right, and then the other thing that it did too is that it has now 24 steps. That indicates that if I move this playhead back, it will move my object at a different frame, and it shows me where that would be on that other frame. So here's frame 1, here's frame 24, and here are all the in-between ones. Okay, so it automatically tweened that for me, and if I were to hit play, it'll do a test. Or if I were to hit return, it would do a test for me. Now, so far everything is the same. This would so far be the same with traditional cell animation with keyframing and tweening if I have one keyframe and an ending keyframe. All right, but this is where it starts to get a little bit different. If I take my tool, my arrow tool, and I sort of hover over that line, you see it gets a little curved line underneath it. Well, if I wanted to drag it, I could change the direction of this path if I wanted to. All right, and that's pretty significant because in traditional animation, I would need to have the object down here to show that it's going to have that particular pathway. But because I'm using computer animated mathematics, it automatically will do that translation for me as part of this line art drawing over time. And so what I can do now is I could even do a little bit more stuff. Like I can take the white arrow tool, and if I click on the ends, you see I get these handles, and so then I could really manipulate the pathway significantly more so that it really changes direction quite a bit. And I can even, pull this like pretty far up here and really significantly change this, right? So that it starts to have a more dramatic representation of how it's going to move its path. And I can draw this even further up like that. So this is really even more significant. So it changes quite a bit. The other thing that I can do in some of the effects is if I choose the path, I can go over here and I can tell it that I want it to rotate. So let's see how, if we have it rotate once, and we can tell it to go counterclockwise. And let's see how that looks. The other thing that I could also do is if I want to go back to beginning here, I can also take my scale tool and I can tell it that I want it to start so that it's like quite small. And then whenever I'm over here at the very end, I can tell it to be a lot larger, right? And so now, if I hit return, you see it's making a lot of changes, but still I only have 2 keyframes. Whereas in traditional hand-rendered animation, I would have to have more keyframes than that to show the change in direction and also to show, the change of size and so forth, and as well as the rotation.
Okay, so the last form of animation that I'll just briefly touch on is kinematics. Kinematics is an even more intricate level of computer-rendered animation in 3D animation. And it's actually not just in 3D animation. It's also like in 2D animation as well, computer-based 2D animation. But basically, it's a study of how the individual parts of a whole will move based on physical laws, and specifically how the joints articulate in relationship to the parent structures. Basically, as an example, like if you were to look at a body, the digits of your finger, for instance, each have knuckles that can bend. Those are articulating joints, but all of those are going to move as a root unit based on where your main knuckle for that one finger would move. And then your entire hand, for instance, would all move based on where the wrist would move. All right. If you're moving your wrist, then all of the other things are going to move as well on the end of that hand. And then, of course, it moves up to your elbow, and then it moves up to your shoulder as the root unit, and so on and so forth. You can also look at it not just as like a body, but also for instance, like a car. So if you were to think about the way that a steering wheel is going to be able to control, the steering column that then spreads out to the axles, and how the wheels can move independently, even though the tires are, rotating and so forth. Those are all going to be based in kinematics. It's basically parts of a whole system and how they move and articulate. Okay, so now let's get to video. All right, we were talking about sort of traditional kinds of animation moving into computer animation, but now let's talk about video, both analog and digital. Okay, but first, let's just start with the analog. All right, in short, analog video is created when a camera records red, green, and blue RGB signals onto magnetic tape, along with audio and tracking, which is tracking of speed regulation information. And just to make sure that you don't get confused, we refer to things as videos today that are like on YouTube, which is digital. But when video originally started, right, it was analog information. Okay, so analog signals are transmitted via radio frequency, and they're picked up by antenna.
The following program is brought to you in living color on NBC.
Okay, so this is a good example of you know, how the radio frequency is picked up by an antenna. This is the old school way, right, of being able to transmit television, for instance. Okay, the most common video broadcast standards are NTSC and PAL, which is, well, NTSC is used in the United States primarily. PAL is basically European format, but the ratio is 4:3 ratio. Okay, there's another one called CCAM, but the thing that you really need to pay attention to are NTSC and PAL. And the reason I bring this up is that you might see these in your format options when using software to produce video. Okay. Okay, and I'm going to just really quickly jump through some different analog cable types. And the reason I'm doing this is in the event that you ever have to use old equipment to, you know, get old footage onto digitized formats. So this is a composite video type. If you've ever seen the little yellow, it's a RCA type of cable. And it combines red, green, and blue channels for video into one single signal. Okay, this is S-video. It has 2 channels for luminance, which is brightness, and chrominance, which is color. Okay, and the next step up would be component video, and it keeps the RGB channels separate for the best quality. Okay, and then there's also a VGA, and it has 15 pins for transmitting RGB analog signals from a computer to a display. This is not digital, even though it's transmitting something from a computer to like a projector or whatever. And on older computers, you still might see this this adapter type on your laptop or something. Okay, so now let's talk about digital video. All right, digital cameras take audio and still frame images. They compress them and then record the information to digital tape or disc. Less common are digital tape recorders anymore, but they do still exist. This information is stored in standard digital data units of measure, like bytes, kilobytes, megabytes, gigabytes, terabytes, petabytes, exabytes, and so on. Okay. Some common digital cable types are Firewire. This is an older video cable, but there are cameras and computers around that are still supporting it. USB 2.0 and 3.0, pretty universal digital delivery connector. It's not necessarily the fastest method to transmit digital audio video, but you know, you can still do it. And you're going to find this on a lot of like Android phones and so forth. DVI, digital video, is purely digital video only. Okay, it doesn't have audio with it. It has video only. It's a connector that's found on a lot of modern computers. Or semi-modern. HDMI is the most current video connector type. It's the highest definition connection, and it carries both audio and video. And Thunderbolt is something that is an Apple specific thing. It's their newest audio video cable solution. Okay, so let's talk a little bit about scanning. So we're going to talk about progressive scanning, interlacing, overscanning, underscanning. Okay. And basically what scanning is it's the way that a picture is displayed and how it draws horizontal scan lines on the screen from the signal. Okay, so first of all, progressive scanning. It draws horizontal lines on the screen from top to bottom in a single pass. All right, this is indicated in a in a display's resolution with the letter P after the vertical number of lines that it's capable of drawing. For instance, you've heard probably of 1080p or 720p, right? 1080p, for instance, represents a 1920 pixel wide by 1080 pixel tall resolution. Okay. If you see something that is like 1080i, for instance, though, that's interlacing. Interlacing draws horizontal lines on the screen from 2 fields and interlaces them together. This is indicated in a display's resolution with the letter I, as I said before, right? And it's the same principle where it's, in this instance, 1080i is the representation of like 1920 pixels wide by 1080 pixels tall. All right, interlacing is generally considered to be a less desirable solution than progressive scanning in digital video, but you'll still find a lot of really nice TVs and stuff that are that use interlacing. So overscanning, all right, what overscanning is the bit that you get outside of what you normally would see like in a television. So to accommodate a digital or a display's bezel, you know, like the little thing that goes around a television, for instance, video is often shot so that it slips slightly under a TV's edge. This means that the TV overscans so that we don't see the borders. So basically it kind of cuts a little bit of it off. You can almost think of overscanning like a digital video bleed, in the same way that we create print bleeds for trimming paper on a printing press. Or a better example even yet would be like if you take a photograph and you want to frame it and put it on the wall, you're going to cover just the tiniest bit of the edges of the picture so that it looks nice and clean. Okay, so because of different ways that things overscan and different resolutions, you always want to have a safe title area. As a result, we leave the outermost 15% of the frame free of titles or text because it can be lost due to these overscanning problems or conversion between like computer, TV, video format translations. All right, and then we get to digital high definition resolutions. So previously we talked about analog, PAL, and NTSC formats before as having a 4:3 aspect ratio. Well, digital high definition video typically has a 16:9 ratio for most TVs and about 21:9 for most movies. Many movies on televisions incapable of 21:9 ratios will have letterboxing or those black bars at the top and bottom. So most TVs have a resolution, for instance, of at least 1080 by 720. And that would be referred, excuse me, this is not right. This would be 1280, not 1080, I apologize. It would be 1280 by 720, I'll fix that. 1280 by 720 as a minimum high definition resolution. The more common size that you're going to see nowadays, at the time of this video anyway, would be a 1080p or 1080i, and that would be 1920 wide by 1080 tall. Okay, so remember the lower one is actually 1280 by 720. Okay, and then just to give you a really quick visual, let's look at this really quick, and it gives you an idea of how far we've come in terms of the massive change in resolution capabilities whenever we went from like analog of, you know, using NTSC, right, and then moving all the way up to 1080, okay, for instance. You can see why things sometimes don't fit right on different translations between formats. So codecs and digital video containers, this is going to be sort of wrapping it up, but what are the differences between these? Well, codec comes from coder and decoder, all right, and that suggests what they do. They code or compress files for storage, and then they decode or decompress files for viewing, sort of like an accordion in a way. All right, so that's a codec. Codecs are not file types. They are simply compression schemes, okay? The most common one that you'll find compatible with most video containers today is H.264 MPEG 4. All right, this is the codec that you should use for projects in this class. So lastly, video containers. They are the architectures that comprise movie file types. Examples would be like .mov for like QuickTime movies, .avi for Windows video. OGG is a web format. It's a standard web format video. FLV you don't see as much anymore, but that's flash video. MP4 is going to be the most common type nowadays that you're going to see. RM would be like real media. You hardly ever see that anymore, and there's some other ones too, but these are file types. The containers are the file types. They also include metadata about the movie. So when saving a video, you have to choose the video container format separately from choosing the codec. And some video containers will only work with certain codecs and so on. But some of the metadata that you might be able to store in a movie, for instance, in an actual file would be things like if it has chapter markers or things like that, you know, that maybe other file types won't support. But anyway, that is going to wrap up this this conversation about video and animation. So please let me know if you have any questions.